Okay, so in this last week of this Math Tools 3 course, we want to focus on something a little bit different. So this section of the course is going to look a lot different than really any of the Math Tools stuff we've done up to this point. So this will cover some material that you would see some of it you would see maybe in like a critical thinking class. Some of it you would see in a class that's typically called something like Introduction to Higher Math or Introduction to Proof Writing or something like that. And it's not normally taken in like a biostatistics department, but it's not always even taken in a math degree. For example, I never took a class that was like this, but I wish I had. So it's really just kind of trying to set us up with some nice tools that'll help us understand some of the more theoretical stuff in statistical theory and probability theory. As the names imply, you're doing a lot of theory, and with theory comes theorems, and with theorems come proving those theorems. So the proofs is kind of what we want to focus on this last week. So how do you go about proving things in a mathematical context? How do you write a proof? How do you you'll more than writing proofs, you'll probably read a lot of proofs. So how do you understand these proofs? So it's kind of my goal here is to kind of give you the tools to understand those more theoretical things that are happening, the more technical details, like why they're doing, the textbooks or your teachers or whoever, why they're doing things the way that they're doing them. Because a lot of times when you read proofs, it can kind of just seem like they're just pulling stuff out of nowhere. It's sometimes hard to follow the logic, um, and that's always kind of true because when you're writing proofs, it's kind of asking you to pull different things from a lot of different areas of math sometimes, and it can be kind of hard to follow. So this week is kind of just trying to ease you into it a little bit more and maybe making some of that more digestible. Now, as I said, you could take an entire class on this kind of stuff, and we're just going to spend 5 days on it. So we're really just getting our feet wet in this subject. Um, but on the other hand, like I said, I never took a class like this. A lot of people are just kind of thrown into proof writing, and it can be kind of difficult. So hopefully, even just with these 5 days, it'll give you kind of a basis so that you can, work with that a little bit better. And in the biostatistics program specifically, you won't be doing a lot of proving stuff. You'll still be doing a lot of calculations, but it might come up every now and again. And again, you want to be able to understand the proofs at least. So I gave a lot of thought to like where we want to start here and exactly what stuff we're going to cover. So I think a good starting point is just going through some of the fundamental stuff in our number system that you probably already know, but maybe haven't formulated it in this way. And this is important as kind of like a foundation because it's used in a lot of proofs. So these are kind of things that you'll just see all the time. So it's just kind of like a hodgepodge of information here, but it's just stuff that will continuously pop up. So again, probably nothing you haven't seen before, but still worth going over. So we'll start by the different sets of numbers that we typically will refer to. So the first one is the natural numbers. Okay. So this is typically defined and written like this. So it's like an N, but it has like a double bar on the left side. If you type it in like in LaTeX, which is the math typing system that we use a lot, that's how like I write all the homework and stuff. You would write it as like math BBN. If you want to see what it looks like, or you could just Google the natural number symbol, for example. This is a backslash, by the way, in front of it. Just if anybody's familiar with that. But the natural numbers is defined as the set. So a set, we've seen sets before, of course. We haven't really defined them, but it's just basically any collection of objects. And typically, in our case, it's going to be numbers. And we'll spend a couple of days just looking at sets because sets are used all the time in like probability, for example, we're taking the probability of sets. So the natural numbers is a set of numbers consisting of 1, 2, 3, 4, etc. Okay, and we use this dot dot dot, of course, to mean that it goes on and on towards infinity. So this is sometimes called the counting numbers as well. So note that this is a little bit different from whole numbers. So sometimes, I don't see this very commonly, but sometimes you'll see some books define the whole numbers with like a W, and there is like some kind of like double bar on one of these. I don't even remember which one. But it does have that symbol, and the only difference between these is that it includes 0. Okay, so it's not common for the natural numbers to include 0. Sometimes you'll read a book and they'll define the natural numbers as including 0, but typically the natural numbers start at 1. And this is, a pretty typical set of numbers to use. And then we expand that out to the integers. Okay, the integers is represented by the letter Z. It's something to do with the name for integers in German, I believe. But this consists of all the negative natural numbers, and it also does have 0 in it. Okay. And then all of the positive natural numbers. So this is sometimes called like the number line numbers, because these are the numbers you would see on a number line. Another common set to restrict ourselves to. This is important because oftentimes, like, maybe we're proving something only on the integers, or maybe we're proving something that's only true for natural numbers, things like that. Sometimes instead of the natural numbers, you might see this called the positive integers, which you'll see like a Z with a plus sign on the top of it. Sometimes you'll see the word non-negative integer, and that typically means the positive integers plus 0. Okay, so non-negative is a little bit different. Non-negative integers would be the whole numbers, basically. So if an author intentionally doesn't want to use the natural numbers because they do want to include zeros, they might call it the non-negative integers. If they just want the natural numbers, they might call it the positive integers. So these things are all just kind of used interchangeably in proofs. Okay. Now, of course, we have the rational numbers. Okay. So the rational numbers is typically represented with a Q with another line over here. And this is going to be the set of all numbers A divided by B such that A is an integer and B is an integer. Okay, so we've seen this set notation before, but just to explicitly say that this line here means such that, and this means is an element of. Okay, we read it as just in. B is in Z, or B is in the integers. So we mean that this is an element of this set of the integers. Okay. So note that B could be 1, so therefore all of the integers themselves are included in this. So far, we would say that the natural numbers are part of the integers. Okay, that's what this means here. This means is a subset of. And we'll get into, like I said, we'll spend a couple of days just on sets, looking at these different definitions, like subsets and stuff like that. But we say the natural numbers are a subset of the integers, which is a subset of the rational numbers. Okay, meaning that the entirety of the natural numbers are included in the integers, and the entirety of the integers are included in the rational numbers. And therefore, by the transitive property, the natural numbers are included in the rational numbers. Okay. So now, the irrational numbers. This one I don't think it's really referred to directly too much by this symbol, but sometimes you'll see this like symbol with an I. It's hard. I can't even really draw it from memory. I think there's a double bar right here, but it's very uncommon to see this symbol in my experience. But this would be the like it's typically just referred to as the numbers like a, such that a is not in the rational numbers. Okay, so it's basically just defined by the rational numbers as the elements that are not inside the rational numbers, and this is how we write that. It's not in the rational numbers. So because of this, it's more commonly written like this, which we read as the complement of the rational numbers, which means all of the numbers outside of the rational numbers. And again, we'll get into the sets specifically, but the complement does need to refer to a larger set. So numbers that are part of a larger set, but not in the set itself. And the larger set it refers to is the real numbers. Okay. And this is typically the place that we live in, right? This is the, we've seen this symbol before for R, and we usually say this is equal to Q union I. Okay, so the rational numbers and the irrational numbers, or we might say Q union Q complement, for example. So the complement on Q is referring to all of the numbers that are real numbers, but not inside the rational numbers. Okay, so if you were to draw it like a set, like if you say, okay, this is the real numbers, and over here we have the rational numbers, then let me write this outside of it. Then outside of that set would be the irrational numbers. Okay. So in irrational numbers, by the way, those would be the stuff like √2, pi, right, e. So these are things that cannot be written as a fraction. So they'll have like an infinite decimal expansion that never repeats. And when you start like really diving into set theory, and these different things, you run into some weird things. Like, for example, that you can show that the irrational numbers, there's more of them than there are rational numbers. Okay. They're much more common in different senses. Okay. So these different sets of numbers are pretty important because oftentimes, like these are very commonly in theorems that you'll read. And even if it's not written explicitly, it's assumed, right? Because it'll say something like you need to put some qualifier on your numbers, like X is a real number, or X is a rational number, or something like that, right? Or maybe it's in some smaller set of numbers, like an interval or something like that. But these will typically appear in some kind of context. Okay. So now I want to get into just a little bit of some common ways that we can write different types of numbers, like for example, the odd numbers and the even numbers. Okay. Odd numbers and even numbers. So of course, these refer exclusively to the natural numbers, right? We don't talk about odd or even for any other number set. Okay. So this is a natural number. Well, let's just say n is an n such that what we would say is that 2 divides n. Okay, so this is how we would read this. 2 divides n. Okay, or you might say n is divisible by 2. Okay, odd numbers would be n is an n such that 2 does not divide n. Okay, so these are common symbols again that you would see. If you just pick up any like math book, usually the first chapter is dedicated to setting up a lot of this stuff. So you'd probably see these kind of symbols in there. So the way we typically would formulate these numbers is that odd numbers Well, even numbers, let's start with those. Even numbers can be written as 2 times n, right? Or maybe 2 times k. We already used n, so let's say 2 times k. K is often used for the integers or natural numbers or whatever. So because even numbers are divisible by 2, we can write any even number as 2 times some other number. And therefore, we can write any odd number as 2k plus 1, because they're just 1 off of an even number, or 2k minus 1. Okay, so we saw this in Math Tools 2 a little bit when we were talking about writing sequences and series and stuff like that. But this is very helpful because anytime we're asked to show something is true for even numbers or odd numbers or whatever, we usually need to invoke these forms. Okay, and then of course we can also think about prime numbers. Another common type of number that comes up. Prime numbers are only divisible by 1 and itself. Okay, so important to note here that 1 is not prime. Okay, 1 is not considered to be a prime number. The main reason for that is just by definition, it's usually just defined to not be a prime number, and that's mostly for something called the fundamental theorem of arithmetic to work out properly, which says that every number has a unique prime factorization, and if 1 was a prime number, then that wouldn't be true. And also, it's just really not very interesting to think of as a prime number, since it's the smallest natural number, so naturally it just can't be divisible by anything else. So if it's not prime, it's called composite. Again, you don't see this word as much. Usually you just say it's not prime or something, but it is technically called composite. Okay. Another thing that comes up somewhat often is the meaning, the definition of coprime. Okay, we say two numbers A and B are coprime if they have no common factors. Can't write two M's for some reason. Common factors. Okay. So the way we typically write this would be A, B equals 1. So this parentheses notation is used for a lot of things. In this context, it's used for the fact that the GCF, greatest common factor of A and B, is equal to 1. But you typically don't write that GCF part. So, context is very important for that notation, right? We've seen it for intervals, we've seen it for points, vectors, now for greatest common factor. So this comes up like in one of the proofs we're going to look at, like this, that the square root of 2 is irrational, for example. That's like one of the most common proofs to look at. It's like the first one that most people look at. So that's used in that. So I think this is a good starting point. I'm just trying basically to think of like the different things that come up in most proofs. So these are very common to see in like different theorems and stuff. But we'll kind of add to it as we go through some different proofs and things and read through them, and different things come up, we'll add to them there. But I think this is a good starting point here.